Hello, Chem30, and welcome to your Q&A for May 19th. I thought I would start off by showing you my new kitten. Here it is. He is. His name is Nix, and he is rather cute, I think, and very cuddly and playful. Yeah, so this is just kind of trying to be clickbait so that you will watch the video with kittens. The video comes with kittens. How can you not watch? Look at the kitten and see the kitten go. All right. So you had some questions. I have answers, or at least I'll attempt to have some answers as we go through here, and hopefully you can learn a few things about questions you had. So first of all, kind of the stuff that was general things for everyone, not specific questions, but I think it's interesting for you to see the answers from your class so you can see where they're at and if how you're feeling is the same as how they're feeling. So the first of all, how are you liking using Edpuzzles for video lectures? 30.4% of you, you're like it better than YouTube. You think it's a better system. Well, 70% of you basically says, yeah, it's the same. So in other words, I'm not seeing any downside for this. So none of you are saying that it's worse than YouTube. So I think it's a good system. What it does for me on my end is I can see that you've watched the video. Okay, so I can actually see how much time you have spent with the video if you've completely watched it. And then also those questions are just nice, I think, to keep you on task for prompts and stuff so you can see what's going on. The kitten is trying to climb up my chair again. All right, so that was that question. Moving forward, how is the workload for Chemistry 30? 8.7% said too much, 91%, most of you said it's about right. I'll be honest, I've been giving you a bit more work lately. What happened is that I thought there was going to be more time in the semester, and I thought that because initially the timeline for high school classes was that it was going a bit later into June than kind of it was supposed to. And then that changed, and now we have a bit less time. So I was slowing down about 3 weeks ago because we had what I thought was more time in the semester. And then it turned out we didn't have that time. So now we're back to speeding up again. We're actually going to, in the unit we're currently in, the chapter we're currently in on acids and bases, we're going to cut out some of the theory, mushy stuff that doesn't carry forward much into university chemistry. We're going to kind of skip that portion to favor more of the organic chemistry, which is a major focus in university chemistry. So we're going to do a little bit of a shift here that in this chapter, actually this week and then going into next week, we're going to be cutting out little bits of theory type stuff that I just feel like is not nearly as important as the organic chemistry that you'll be learning next unit in order for us to be able to lighten up a tad in terms of workload. So yeah, pretty much until then, you've had the kitten again, the full course experience for Chem 30. We've covered almost everything, maybe sometimes in a little bit less depth or difficulty, but pretty much covered everything. And here we're actually going to cut a little bit out at the end of chapter 16 in order to save a bit of time. And like I said, because it does not carry on as much to university chemistry, it's not as critical that you get that information. All right. So average amount of time you are spending on school stuff, answer for this, kind of most of you would be between that 3 to 6 hour amount. A few people are greater than 6, and a few people are 1 to 2. So I bet that probably really just kind of depends on your course load and what you're looking at for the courses you're taking right now. So it really varies. I got to get rid of this kitten. He's just trying to climb up like crazy. So I'm going to let him out of the room. Okay, so that's where people are at. Again, I think it's just interesting for you to see where the class is at in terms of their workload to make sense of your own. Do you prefer cats or dogs? How dare you? Most of you seem to prefer dogs. It is what it is. I have both, but I don't tell my dog this. I prefer my cats to my dog. Yeah, my dog is very needy and anxious. Okay, could you please go over question 5 from equilibrium theory / representing equilibrium? For sure, here is question 5 from that worksheet. Let's quickly go through it so you can see what the answers are and how things would look for this. So If I were going to do this particular one, hydrogen and nitrogen gas will yield approximately 10% ammonia. I would have H2 gas plus N2 gas. Then I'm going to have equilibrium arrows here and then ammonia as NH3 gas. And then what I would do is put approximately 10% over top of that arrow since I know the approximate yield. That squiggly, if you haven't seen that before, is just saying approximately equal to, right? The approximate number. Sulfur dioxide and oxygen produce sulfur trioxide and reach a product favored equilibrium. So I would have SO2 gas and oxygen O2 gas produce. I should balance this one. Sorry, I should have had a 2 here and a 3 here going back to A. SO2 and O2 produce sulfur trioxide, SO3 gas. And this is product favored, so I'm going to put a greater than 50% on this just to show that most of it ends up as products instead of reactants. Again, for balancing, I'm going to need a 2 right here and then a 2 right here to make that work. Zinc ion and silver metal are mixed and the equilibrium is reactant favored. So I have zinc ion, Zn2 positive aqueous, and silver metal is Ag solid. This is going to react to form Ag positive aqueous and Zn solid. In order for us to balance charge, I'm going to need 2 on this and then 2 on this. It's reactant favored, so I'm going to put less than 50% on that one to show that it's a reactant favored equilibrium. And then finally, carbon burns completely in excess oxygen, so I just have C solid plus O2 gas. It burns completely in excess oxygen, so I'm going to get to CO2 gas. I'm going to use a quantitative arrow for this to show that it is a complete reaction to products. Again, if it says completely or quantitatively, that means that I'm not using equilibrium arrows. I'm using a full-on arrow from the reactants going to the products. So that was question number 5 from the equilibrium theory and representing equilibrium worksheet. The other questions, or some of the other questions I had to do with Le Chatelier's principle. Kind of confusing for a lot of you. So I had 4 questions that kind of came down to Le Chatelier. Generally, like, don't get how it works, especially if it's about a concentration in a chemical being added or taken away. And then also 2 people mentioned that pressure and volume changes were confusing in terms of the shift from that kind of a stress. So let's talk through Le Chatelier and go through an example, and hopefully that will clear it up. So Le Chatelier's principle, summary in a nutshell, here's what's happening. A chemist applies a stress. So they are going to do something to one chemical or one property of the equilibrium. So that's either a temperature change, a volume pressure change, or a concentration change. That is the stress that the chemist is applying. And then as a result of the stress, the equilibrium will shift. So the chemical equilibrium is going to shift left or right in order to oppose or fight the stress. So stress is applied, that's the before, and then equilibrium will shift, that's the after. Okay, and the equilibrium shift again occurs in order to fight the stress that was made from the chemist, to do the opposite. And the reason why this happens is that it's trying to keep Kc essentially the same. So if the chemist applies a stress of upping a concentration, then as a result, it will shift in the opposite direction in order to keep Kc values the same for that equilibrium. And I mean, don't worry about the math of this. Just know that whatever the chemist does to the stress, the equilibrium will shift to oppose that stress. So here's an example. I have CO2, H2, CO, and H2O. So I have these 4 chemicals here in equilibrium. And then this is an endothermic equilibrium based on the plus 42.0 kilojoules. I'm realizing now that this is actually a bit of an unfortunate example based on the fact, and this is straight from your workbook, but based on the fact that it has even amount of gases. So what we're going to do, let's talk through this, okay, and then let's change it in order to make it better as a volume question. So when I look at a volume change, I would look at how many moles of gases I have on both sides. And here I have 1, 2, 2 moles of gases here in reactants, and 2 moles of gases here in products. So what that means is no matter what I do to this equilibrium in terms of a volume or a pressure change, it can't shift to oppose that change because both sides have the same moles of gas. So it can't go in any direction to lower or raise the pressure to fight what the chemist did with the stress. So now that we've established that, we're going to change it from the question in your book. And we're instead going to make H2O a liquid. Now this changes things because now I have 2 moles of gas in reactants and only 1 mole of gas in products. So this now makes it a more interesting question for a volume change. So here's the stress, and then we're going to figure out the shift that happens as a result of that stress. So if I decrease the volume of the container, so volume of the container is going down, and if that happens, if I'm compressing the container, then the pressure is going to be going up. So that's what the chemist is doing. They're increasing pressure. So now the question is, what can the equilibrium do in order to fight the change the chemist made? So if pressure is going up, then what can happen is that the equilibrium can shift right, which lowers the amount of gases that are in the vessel. Because remember, all of these chemicals are together at equilibrium in the system, right? They're all in the same container. So if I increase pressure, it can shift to the right, turning 2 gas molecules into just 1, which will cause the pressure to go back down. So chemist increases pressure, equilibrium shifts to bring it back down, so the shift would be to the right. So what would that do for carbon monoxide? Well, if I'm shifting to the right, then that's going to cause carbon monoxide to go up because it's making more product, and carbon monoxide is a product. So the change in carbon monoxide would be that it would increase or go up. Do not confuse the stress to the after all change in concentration. This is the cause, and then this is the effect. Okay, so the cause of the shift is the stress, and then it shifts to the right, and that causes the effect of increasing carbon monoxide concentration. Don't confuse those two things. All right, if I'm adding heat, energy is a reactant in this because of the fact that this is an endothermic reaction. So as a result, energy would be a reactant. So if I am adding heat, I am increasing the energy. So what will the equilibrium do? It will shift in the direction that lowers the temperature again, that lowers the energy. So by shifting to the right, by doing the forward reaction, that's an endothermic reaction. So we'll bring the temperature back down as a result. So again, the stress is temperature is increased by the chemist, and then the equilibrium shifts in the direction that brings temperature back down. And that would be the right direction because that's the endothermic direction. So we'll shift to the right in order to decrease the temperature again. So that again causes an increase in carbon monoxide. Remove H2O. Remember that this is now a liquid with how we wrote it. And again, this does not match your workbook because we changed the equilibrium reaction to be water as a liquid instead of a gas. If I remove H2O, what does it do? Nothing. It doesn't do anything anymore because of the fact that it's a liquid, so I cannot change the concentration because it is the only liquid. So because it's not involved in the equilibrium Kc expression, it's not going to cause a shift. So no change in CO. If I add CO2, So I increase carbon dioxide. Equilibrium will shift to bring it back down. So that means that it will shift to the right, which uses up the carbon dioxide. Okay, so add CO2, that's the stress. CO2 goes up. Equilibrium shifts to the right to bring it back down. So it's going to be, again, a right shift, which will cause an increase of carbon monoxide. Okay, place reaction vessel in ice. So again, I have energy as a reactant. If I'm placing it in ice, I am lowering the temperature or the energy. So it's going to shift to the left in order to bring the temperature back up. Okay, so it's going to shift in the direction that's exothermic in order to increase temperature, to fight the stress of lowering temperature with the ice. So what will that do? That will decrease carbon monoxide because that is turning product, carbon monoxide, into reactants in this reaction. Add a catalyst. As you know, catalysts cause no shift. It does not shift at all, okay, because catalysts do not change anything for an equilibrium. They might help equilibrium get reached faster, but they don't change the position of the equilibrium. Okay, if I decrease pressure in container, so I have again two gases here, one gas and products. If I decrease the pressure, so pressure has gone down, it's going to shift in the direction that brings pressure back up. So how that goes is because I have two gases here and one gas here, it would shift to the left because then I have more gases present, which will increase the pressure because I'm essentially like increasing gas molecules, so pressure would go up, right? So stress of decreased pressure from the chemist, equilibrium shifts to make more gases and increase pressure back up again. So direction of shift would be left, which would result in a decrease of carbon monoxide as a result. If I remove hydrogen, so I bring down H2, it's going to shift left to make H2 again, to bring H2 back up. Okay, so if I remove hydrogen, it's going to be a left shift. The equilibrium will shift in order to oppose or fight the stress made by the chemist. So chemist removed H2, equilibrium shifts left to make more H2 and bring it back up again. So change in CO, this would decrease because as I shift left, it's using up carbon monoxide in order to make reactants, right, in the left shift. So again, as I talked about in the Le Chatelier lesson, equilibrium systems are like a bratty child. Whatever you do, it will do the opposite. If I tell a kid, hey, don't you eat those vegetables, it's a bad example. They still wouldn't eat the vegetables if it's my kids. But if I said, don't eat those peas, then they're going to start eating the peas. Right? So whatever the chemist does, the equilibrium is going to do the opposite, shift to oppose the change. All right, hopefully that helps. Hopefully that clears up Le Chatelier. Let me know if you're still confused and also pop on a Zoom, right? Come into the tutorial on Wednesdays, Thursdays. Wednesday is Science 9, Thursdays. I could also do a tutorial an additional day if there's enough demand for it, and then we can work it out for that from there. All right, another question. The first ice chart in the Edpuzzle video was messed up. Yeah, totally was. Thanks, Harrison, for actually like bringing my attention to this first of all, and then I think I left a comment on the lesson. I read this wrong. So here's what happened. It said that a reaction vessel was filled with NO2 to a concentration of 2 moles per liter. And at equilibrium, it is found that there is 0.250 moles per liter of NO. But I read that as 0.250 liters of NO2. So this should have actually been over here, okay? And as a result, that would have been the equilibrium, and then that changes all the values. Now, the work I did was good if it was the opposite question of 0.250 was the NO2 concentration. So maybe what you want to do as you go through this example, if you haven't already or you were confused, is just actually change in your workbook the question to this: 0.250 moles per liter of NO2. It's still a good question. And then that's what I went through. But unfortunately, and I'm sorry about this, I read it wrong. Once the videos are made, in order to record that example only and then splice together the videos takes such a huge amount of time that at this point, if I'm being horribly honest, with the amount of content I have to make for this class in Science 9 and the work that this involves, I would have to give something else up. So it's kind of just positives and negatives. It hasn't been worth it for me to fix this particular video right now at this point because I just don't have the time. But it is something that I plan to do in the future because it is a mistake. But yeah, so treat this instead as there is 0.250 moles per liter of NO2. And then if you do that, the work for the question is completely and totally fine. And it's still a good example, but I did make a reading error as I did this example, and I apologize for that. So there are also some questions on ice charts, just confusion of can you do another example, especially given that I messed up on that first example on the YouTube video, probably good to do another one. So I picked number 4 from your workbook. I think it's nice for you to be able to look at a question that maybe you've already attempted or that is in front of you for an example. So let's try this one out, go through the motions. It is a bit of a harder one because it involves X, unlike a lot of the ice charts that you'll be facing, where you don't need to use an X. This one you do. But let's work through it and see how it goes. And I want you to keep in your mind separate, are you struggling with the ice chart concept or are you struggling with the math and the algebra, which is 2 separate issues, right? If you understand ice chart, that's fantastic. Maybe your work needs to be more with understanding algebra and the math. So yeah, but let's go through an example, see how it goes. So for question number 4, quickly, 0.40 moles of I2 and 0.40 moles of Cl2 are placed in a 1 liter flask. So important to, first of all, realize that I need to calculate the concentration of that, which I just take 0.40 moles and divide it by the 1 liter in order to get a concentration. And then I get 0.40 moles per liter. So just that we realize that the mole value is not a concentration, but if I divide it by the vessel volume, then I get my concentration for that. So let's build our ice chart and then figure out everything that we have. So I have I2, I have Cl2, and I have ICl as a product. So for initial concentrations, and then my change in my equilibrium, for I2, I have 0.40 moles per liter. For Cl2, I have 0.40 moles per liter based on the question. And then for ICl, I don't have any information, so we're going to assume that the initial concentration for that is 0 based on the lack of information we have. Okay, so now we got to think, is I2, Cl2, or ICl going to be going down? And the only thing that can go down at this point is I2 and Cl2 because that's what I have something of. The only thing that ICl can do is it can go up. So I2 and Cl2 will go down by some amount X, right? We don't know how much X is. We're going to figure that out. But we know that these are going to go down or decrease. And then ICl is going to be going up. But because it has a coefficient of 2, it's going to go up by 2x, right? Instead of just 1x. So I'm using the molar ratio of 2 to 1. So it's going to go up twice the amount that I2 or Cl2 will go down. That means that equilibrium concentrations will be 0.40 minus x for I2 and Cl2. Well, for ICl, the answer for this for equilibrium is going to be 2x. So my Kc expression for this is going to be ICl squared over, excuse me, I2 and Cl2, right? Products over reactants to the power of their coefficients. This is equal to 10.0. So now we got a bunch of math we're going to have to tackle here. So I'm going to go to a new page in order to write this out. That means that 10.0 is equal to 2x squared, the ICl, divided by 0.40 minus x multiplied by 0.40 minus x. So all I've done here is plugged in these equilibrium expressions, right, for my different concentrations into this in order to kind of now solve for x. And if I can solve for x, then I can solve for equilibrium concentration of ICl. So I need to realize that this is equivalent to writing 2x over 0.40 minus x squared. So I've got 0.40 minus x underneath of 2x, I square that, and that's the same as this. And the reason why is if I have 0.40 minus x multiplied by 0.40 minus x, it's the same as writing 0.40 minus x squared. And then if both things top and bottom are squared, I can just write it like this, and that still works. So now what I have is I can square root both sides in order to simplify this. So the square root of 10.0 is equal to then 2x over 0.40 minus x. Okay, so now I'm at this point where I've got 2x over 0.40 minus x, and now what I can do is I can simply take the square root of 10, so second square root of 10.0, and I end up with a value for that I can now work with in order to solve for some stuff. So I have 3.1623, we're going to keep a few decimal places here, is equal to 2x over 0.40 minus x. So now I'm going to multiply both sides by 0.40 minus x. I end up with 3.1623 multiplied by 0.40 minus x is equal to 2x. Now I'm going to multiply this through my binomial in order to get the two terms. So 3.1623 multiplied by 0.40 is going to give me an answer of 1.2649. So 1.2649 minus 3.1623x is equal to 2x. So now I can move all of my x's over to one side, divide, and solve for x. So I have 1.2649 is equal to positive 5.1623x. All I've done is added 3.1623x to both sides there in order to get that, which means x is equal to 1.2649 divided by 5.1633. So just plug that into my calculator here, divided by 5.1633, and I end up with an answer of 0.2449. So let's go 0.245. Okay, so that's what I have for my x value, but I'm not done yet. I'm going to go back now to my ice chart and work out what everything is going to be. So if I have 2x, then all I have to do is take 0.24498, multiply it by 2, and I can have my answer in 2 sig digs. So my ICl concentration in 2 significant digits will be equal to 0.49 moles per liter. Now what I should do is go back to my stuff here and make sure that everything is good for my Kc working out to 10. So if I take 0.4 and subtract from that my x value of 0.245, this is equal to 0.155. So now what I have is 0.49 squared. All right, so I'm just plugging in my concentrations here. I probably should write this out. Kc is equal to then 0.49 squared, my ICl concentration, divided by 0.155 times 0.155. And we'll just make sure that that works out to the ballpark of what we expect to be for Kc, which is 10 from the question. So divided by 0.155, sorry, times 0.155. Close those brackets. Okay, press enter, and I'm right at 10, 9.99. So that value is good. So my ICl concentration at the end of the day is 0.49 moles per liter. So a bit of a tougher question because it involved x and quite a bit of algebra. The big thing is, can you set up this ice chart? One thing that students often have a hard time with is the fact that Reactants and products always have to have an opposite sign for the change, right? If one's going down, the other has to go up. So make sure that when you're doing your ice chart that is true, that reactants, if they're positive, then products are negative. And if products are negative, then reactants should be positive. I said the same thing twice. If products are positive, then reactants should be negative. So make sure that is true for the change and that the change is also obeying your molar ratios. The change is the part that is the most confusing in ice charts. I feel like the rest is relatively easy, but coming up with the change can be tough. All right, that was it for the Q&A for this week. Enjoy the rest of your day.